trinomials come up. So remember, trinomial just means 3 terms. Let's do a quick example to see how this breaks out. So where these come from is if I have 2 binomials being multiplied times each other. Distributing like we did on class on Monday by FOILing out, first term would be x squared. The outside term would be plus 3x. The inside term would be plus 2x. And the last term here would be plus 6. And then we would combine our like terms, right? So x squared plus 5x plus 6. Actually, you know what? I want to write this up top. So I want to write underneath this. So x squared plus 5x plus 6. So what we want to do is take this and break it back down to the factoring, right? This is the forward direction of multiplying out. Factoring is the reverse direction of breaking it down into those 2 products. So the question is how do we do that? And the answer actually lies kind of in this middle step here, which is if we wanted to, we could say, oh, okay, this is x squared plus 3x plus 2x plus 6. If I ask you to factor this, if it's in this form, we could go through and just do a factor by grouping, right? We could say factor out an x, which would leave me with an x plus 3. Here we could factor out a 2, which would leave me with an x plus 3. And so what we have here is x plus 3, x plus 2, which is exactly what we wanted, right? We want to factor this down. But the question is if I was given this, how do I know that I'm supposed to break this up into 2 and 3? Why didn't I break it up? I could have broken it down into x squared plus 4x plus x plus 6. I could have broken it down in a different way. How do I know that 3 and 2 are the exact way that I need to break this down to get a factor by grouping? And there's a method for this. Let me put it this way. There are a lot of methods for this. I'm going to show you the way that I find the easiest. But if you go digging through YouTube, there are many, many different ways to basically figure out how to break down this piece. They're all valid, and if you want to use them, feel free. But that being said, all the work I'm going to be doing is going to be using this method. Okay, so we're going to take a little bit of an aside, and we're going to look at what we call a diamond problem. Diamond problems are pretty much just like little puzzles, which is you're going to have a number up top and a number on bottom. And what you're going to figure out are what are 2 numbers that multiply to the top but add to the bottom. So an example of this, of a diamond problem here, would be like if I have 12 and 7. So we're looking for 2 numbers that multiply to 12 but add to 7. So here would be a fairly easy one. This is just going to be 4 and 3. 4 times 3 is 12. 4 plus 3 is 7. Pretty straightforward. I'm just going to do a couple of these. We have something like 16 and 8. Multiplying to 16, adding to 8, that would be, oops, I want to color code these. 4 and 4. Because multiply to 16, add to 8. We could also have, there's one case that's kind of weird. We could have something like 7 and 8, which is we want 2 numbers that multiply to 7 but add to 8, which for a second seems weird, but if you just think about the idea of 7 and 1, multiply to 7, add to 8. And we will sometimes have negative numbers on these. So if we have something like negative 10 and positive 3. Well, for multiplying, we know we have to have, if we multiply to get a negative, that means I have a positive and a negative number. And if we think about this, the only things multiplied to 10 are well, 10 and 1, but that doesn't give me a 3. We could go 5 and 2, where the 5 is positive and the 2 is negative. Those multiply to negative 10, but add positive 3. So this is in essence what a diamond problem is. And I'll show you in a second how we're actually going to use these to go back to factoring. Positive 5, negative 3. But are there any questions on this? Okay, so how do we actually use these to factor? So when we're dealing with these trinomials, that means they're going to have 3 terms. So there's always going to be an A term, a B term, and a C term, where A is the number in front of the first term, B is the number in front of the middle term, and C is the number on the last term. And the way it's going to work is the top of your diamond is always going to be A times C. So this is 1 times negative 35. Well, that's negative 35. And your B term is always going to be on the bottom. So in this case, that's going to be 2. So now we have my diamond set up. I want 2 numbers that multiply to negative 35, but add to positive 2. So multiplying to 35, you're probably going straight to 7 and 5. Oops, actually, let me color code these. 7 and 5. And we need a negative here since we're adding to a positive number. That means that my bigger number is positive, which means that my smaller number is negative. I'm going to do one more thing here. I'm going to scoop this up. I can scoop this up. Okay, so what these numbers tell me is this is going to be how I break up my middle term, because we want to do that thing that we did at the beginning, which is I want to do factor by grouping. In order to do factor by grouping, I need 4 terms. So we're going to make 4 terms by breaking up this middle term according to these numbers. So what that means is we're going to have x squared, and then looking at my first one, we're going to have plus 7x. Then minus 5x minus 35. So this middle term we broke up into 7x and negative 5. We broke them up according to the diamond. And note, we still have the exact same expression because if I combine my like terms, that gets me back to 2x. We haven't changed the actual value of anything. All we've done is made it so that there are 4 terms, and we can now do our factor by grouping. So on the first 2 terms, we've got a common factor of x, and factor that out, that'll leave me with x plus 7. On my second 2 terms, we have a minus 5, and if I factor that out, that'll leave me with x plus 7. And here's how we know we did the work right, because we have this common binomial to factor out, and then if we kind of work that out, we're left with x minus 5. Any questions on this? Okay, so if you're very, very keen-eyed, you might have noticed something. Oops, not what I wanted. That the numbers here are exactly the same as the numbers right here. So do I really need to go through into all this factor by grouping work? And the answer is, in this case, you didn't, but there will be cases that you have to. The general rule of thumb is we talked about these numbers A, B, and C. If your A value happens to be exactly positive 1, then the numbers on your diamond are exactly the final answers on your final factoring. If A is any other number, you have to do the full factor by grouping. So this is kind of a sometime shortcut. If the term in front is exactly 1, that first term in front is exactly a 1, then the numbers on your diamond are exactly your factors. If it's any other number, if it's -1, 2, 5, 7, 143, any other number, we actually do have to go through and do the full factor by grouping. So let's look at an example where the full factor by grouping is necessary. But just before I move on, any questions on this example? All right. So let's do once again. Prompt is going to be a factor. So remember, we have an A term, a B term, and a C term. On top of my diamond is A times C, so that's 6 times 2, which is 12. And on the bottom of my diamond, we have 7. So we're looking for two terms that multiply to 12, but add to 7. So in this case, that would be, well, multiplying to 12 would be 4 and 3. All right. So breaking that up, that's going to give me 6x squared, going off my diamond, plus 4x, plus 3x, breaking up that middle term, and then plus 2 at the end. Now we have our 4 terms. Now we can do our factor by grouping. If we look at that, we can pull, both of those have a factor of 2 in them. They also both have an x on them, so we can factor that out. And we're left with 3x plus 2. On the second two terms, they don't have anything in common, but just like we saw before, this here is exactly the same as this binomial here. So it turns out we don't actually need to factor anything out. So what we'll just do is we'll factor out a positive 1. You're left with 3x plus 2. So now we have this common binomial of 3x plus 2. So we're going to pull that out. And then what we're left with is a 2x plus 1. So note here, the values of 4 and 3 were not the values at the end here. And in fact, 4, I mean, technically you'd be like, oh, well, there's a 3 here, but 4 does not show up anywhere in this set. So once again, the trick is, if the number in front is a 1, you can say that the numbers on the diamond are exactly the numbers for the factor. But if it's any other number, then you will have to go through and do the full factor by grouping. So here would be the case, here would be the example where A does not equal 1. That first value was other than 1, so we had to do the full factor by grouping. Okay. Any questions on this? All right, let's do another one of these. And we're going to throw some variables in here that are not x. So let's say we have 2x squared minus 7xy plus 3y squared. So starting this off just like last time, we're going to have an A, a B, and a C. So multiplying that out, up top we have A times C, so that's 2 times 3, which gives me 6. And on bottom, we have a B term of negative 7. So we have to multiply to a positive number, but add to a negative. Well, the only way to multiply to a positive number with negatives involved is that we're going to have, both of these have to be negative numbers. Have to be. And the only way for this to work out is if we have negative 6 and negative 1. Those multiply to be positive 6 and add to be negative 7. Okay, so that's going to tell me how I break up my middle term. So let's break it up. That's going to be 2x squared minus 6xy minus xy. Technically, it's a 1xy, but we can just kind of drop the 1 like we usually do. And then we have plus 3y squared. Okay. So looking to see what can we pull out of the first two terms. These both have a 2 on them, and they both have a x on them. So an x on them. So kind of dividing these each by 2x. It's going to leave me with x minus 3y. And then if we look to see what do these both have in common on the second term, they both have a y on them. So if we divide these each by a y, that's going to give me negative x plus 3y. And we run into that same thing, which is these are almost the same, except the signs are wrong. So that means that I'm just going to take this second term and make it a minus. And that'll allow me to flip that to a plus and that to a minus. And now we have the exact same binomials. So now we can work this out, pull out the x minus 3y. And then once that's factored out, we're left with 2x minus y. So there's a slightly more advanced one. Like I said, it kind of works out more or less exactly the same. The only difference here is we're dealing with more than one variable here. But when it comes to factoring, we're just always looking to see what do they have in common. Alrighty. Any questions on this? Okay, the other thing that might sometimes be useful is to look to see if there are any greatest common factors that you can pull out beforehand. So if you're asked to factor 12x squared plus 36x minus 48, You could go straight to the diamond and say, all right, 12 times negative 48 gives you negative 576. And we've got 36. And you can kind of be like, all right, what are two things that multiply, divide 76, but add to 36? And you can kind of screw around with that. But one thing you kind of want to look out for is, well, these numbers are huge, kind of a pain in the butt. And if we look, each one of them is divisible by 12. So before I start going to my diamond problem, what I can do is I can pull out that 12, and I'll be left with x squared plus 3x minus 4. And now we're doing a much, much simpler expression. So multiplying a times c, we've got negative 4, and my b term here is 3. So obviously much, much easier to deal with the smaller numbers. So if we look here, we want to multiply to negative 4. So that means we've got a positive number and a negative number. And since the bottom is positive, that means we've got a bigger number that's positive. So that's 4 and negative 1. Actually, I'm just like that. And since we have a 1 in front of the x squared, we don't have to do the full factor by grouping. We can go straight to this is going to factor down into these two numbers of x plus 4 and x minus 1. We can skip the factor by grouping because my a term here was 1. And then this 12, we'll just bring that down. Okay. Any questions on this, anybody? Alrighty. So that's going to lead us into our last section for today. 5.6. Special factoring formulas. So what these are kind of, the name says it all, special factoring formulas. But really the way to kind of treat these sections is these are shortcuts that kind of allow you to bypass some work. They're not necessarily mandatory. You can always go back to just about everything we do in this section can eventually go back to, doing this diamond method for all of these problems. But if you can recognize that you have a specific type of problem, you can bypass some of that work and save yourself a little bit of time. So we're going to look at 4 special cases. And the first is if I asked you to factor something like this. Now, right out of the gate, we've got some issues, right? We've got only 2 terms. We can't factor, this doesn't have a variable on it. This isn't divisible by 6. It looks like right out of the gate that we can't factor something out. Oh, I should say this as a note. A little bit of vocab. If a polynomial can't be factored, that's what we call a prime polynomial. Just like with numbers, right? If you can't break down a number, we call that prime. If you can't break down a variable expression, we call that a prime polynomial. So initially, this looks like it's a prime polynomial. We can't factor it down. We can do a little bit of a cheat, though. Normally, what we're just looking at is 3 terms. I can actually kind of cheat a little bit and put in a middle term here and just make that middle term 0. And say, well, there's this imaginary middle term. It just happens to be 0. Now, this is not something you're going to have to do all the time. And once again, we're going to have a shortcut for this. But kind of going through how this would work out. Well, once again, we have a 1 in front. So we've got negative 36 from the 1 times 36. And my bottom here is 0. So now we're looking for two terms that multiply to negative 36 but add to 0. Well, if they add to 0, they have to be the exact same number in terms of positive and negative. And in this case, positive 6 and negative 6. And once again, we have a 1 for my a term, so we can go straight into this. We'll factor into x plus 6, x minus 6. So the kind of thing to note and how we can kind of write this as a general formula. What we have here is the reason why we had the 0 term is that the positive 6 and the negative 6 added together to cancel each other out. And that's always going to be the case when you've got what's called this is our first formula, a difference of squares. Meaning you've got something of the form a squared minus b squared, which is kind of what we had here. This is a perfect square. This is a perfect square. So once again, you can always go through and add the 0 term and do the little diamond here. But if you have something of the form a squared minus b squared, this will factor into a minus b, a plus b. And if we look at that last problem, once again, we had x squared minus 36. Well, this is a perfect square of x. This is a perfect square of 6. So we could have just said, oh, that's going to factor into x plus 6 and x minus 6. Questions on that, anybody? All right. So, pretty much all we're doing is breaking this thing down in terms of their perfect squares. So if we have something like 4x squared minus 81. This is a perfect square of 2x. This is a perfect square of 9. So we have two perfect squares with a minus symbol, so we have a difference of squares, so we can go straight into saying this is going to be 2x plus 9, 2x minus 9. And just go straight into a factoring shortcut as opposed to doing, all right, I'm going to write this as 4x squared plus 0x minus 81, and then doing the full diamond on that, which would actually be kind of messy. All right. Any questions on this? One thing to keep in mind is that anytime you have an even power, if I have something like x to the 6th, that can always be written as a perfect square because that can be written as x cubed squared. So anytime you have an even power, all even powers are technically perfect squares. So if we have something like 25 minus 49x the 6th, it has to factor. This is a perfect square of 5. This is a perfect square of 7x cubed. So we could factor this into 5 minus 7x cubed, 5 plus 7x cubed. And note, even though we normally like to put the variable in front here, be careful here, since this is what's in back, the x is in back, that means when I do the factoring, we have to keep that same order. You could reorganize this if you wanted to. You could say, you could rewrite this as negative 7x cubed plus 5, and sorry, negative, yeah, and 7x cubed plus 5 if you wanted to rewrite it in terms of highest power. But honestly, this is probably how, we're going to kind of follow the factoring formula directly. That's what the answer is going to look like on a multiple choice test. Okay. Questions on this, anybody? All right, let's look at one more of these factor by groupings. Or sorry, not factor by groupings, I apologize. Difference of two squares. Okay, so here we have x to the fourth is a perfect square of x squared. 16 is a perfect square of 4. So we can factor this into x squared minus 4 and x squared plus 4. But in this case, once again, the question is, can we factor again? Turns out we've got another difference of squares. When I factor this down, we still got some more squares. This is a perfect square of x. This is a perfect square of 2. So I could factor out just that first bit as x minus 2, x plus 2. The x squared plus 4, this formula and this sub trick does not work if you have a positive number. We can kind of look at that real quick. If we had like x squared plus 0x plus 4, and we tried to do a diamond on that, positive number and 0 is what we would have. There's no way to get a positive number because they have to be the same sign. And if they're the same sign, there's no way we're going to get a 0 on that term. So as it turns out, the positive part of it is prime, so we're just going to carry that along for the ride. So here's your full factoring. So there are times when difference of squares leads to another difference of squares. Just be on the lookout for that. But note in general, if you have something that's of the form a squared plus b squared, in general, that's prime, which means it can't be factored. At least using this trick. You might be able to pull out, if we had something like, 3x squared plus 9x, we could definitely pull terms out of that, but we can't use this factoring of perfect squares, this difference of squares. Alrighty. Questions on this example? Alrighty. So just like with squares, we're going to go one more. Turns out there's actually, so if we have a squared minus b squared, that factors into a minus b, a plus b. Turns out there's also one if we have a cubed minus b cubed. We can factor that into, it actually starts off as a minus b. The second part's a little messier though, and this is where I'd kind of recommend having this formula just kind of written down. At the end of this section today, I'll kind of write down everything in a nice little list that you can kind of use for your homework and for your quizzes and your exams. But if it's cubed, so here we have the difference of squares. I'm going to just write the names down. Difference of squares. Here we have a difference of cubes. So that would be a minus b times a squared plus ab plus b squared. So the second bit's a little messier. And it also requires, if you don't have your cubes kind of memorized, this is also something to kind of keep on the, have on a little 3 cubed, 4 cubed, 5 cubed, and 6 cubed. Really, you don't need your cubes past 5. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and 6 cubed is 216. So it's kind of something to keep in your back pocket. So how does one of these work? Well, let's say we have something like x cubed plus 8. Kind of like how we did it with squares, except we're doing it with cubes. This is a perfect cube of x. This is a perfect cube of 2. Oops, pardon me. I wanted this to be minus, pardon me. So going to my formula, this is going to be my a value. This is going to be my b value. So here we have a minus b is just x minus 2 times a squared, so that's x squared, plus a times b. So I'm going to write this literally x times 2, that's my a times b, and then plus b squared. But we're going to simplify this out to be x minus 2 times x squared plus 2x plus 4. Now the question comes is, can I factor this? That looks like one of my trinomials that we were working on earlier. Short answer is no. This, so long as you didn't, if there were any common factors to pull out at the beginning, you could do that. But in general, this second trinomial will always be prime. So really you just have to kind of work down on using the factoring formula. And once you do that factoring formula, you're good to go. You finish the problem. Let's do another one of these. Again, the prompt here is to factor. So this first term is a perfect cube of 27 is a perfect cube of 3x. And 125 is a perfect cube of 5y. So let's see, can I get my, let's see if I can get my formula on here at the same time. First we have a minus b, where this is my a, this is my b, so we have 3x minus 5y. Actually, write this a little bit bigger. Actually, you know what I'm going to do? I'm going to slide this up a little bit.
I'm sorry to interrupt. Before you go faster, or before you go more into the problem, you know how you have 27x to the third and then 125y to the third? On the one above it, it was x to the third minus 8, but it didn't have to the third at the top.
Well, 8 itself is already a perfect cube, right? 8 is a
Oh,
cube of
okay.
2,
Okay.
right? So this is only a specific thing. Like if this had been anything different, like if this had been a 9, we couldn't do this formula because this is my list of perfect cubes.
Oh, okay.
Likewise, if this had been a y squared, that's not a perfect cube, so I can't use this formula. This formula only holds when both things are both cubes. Does that make sense?
Yes.
Great.
Thank you.
No problem. Okay, so going through the formula, we have a minus b. So my a here is 3x minus my b here is 5y. Here's when you need to be careful. We want to take a squared. That's the entire term of a. So that's, here's a squared. So we'll have to simplify that in a second. And then we're going to have plus a times b, so that's 3x times 5y. And then lastly, plus b squared. So we're just going to simplify this. So 3 squared is 9. So we have 9x squared. 3 times 5 is going to give me 15 xy. And 5 squared is 25 y squared. So here we have a full factor. Any questions? All right. Now, before, when we had a squared plus b squared, that was prime. As it turns out, if you take this up to a cubed, you actually can factor this out. And here's going to be the formula for that. We basically flip two signs. The old formula we had, if we have a cubed minus b cubed, that was a minus b times a squared plus ab plus b squared. Basically, as we change this sign here, that flips that sign, and it flips that sign. So the way I like to remember it is whatever your starting sign is here, that's your sign there. A squared is always positive because squaring a number always makes it positive. B squared is always positive, so it's going to be this middle term that's going to flip the signs because we always want somewhere to be an opposite sign, and that's where it is. So, like I said, the work for these is exactly the same. All we're doing is just flipping the signs. So if I have something like, let's see, what's one? What we have done 64 yet. So let's say I have 64 y cubed plus 1. (64y) is a perfect cube of 4y, and 1 is just a perfect cube of 1. So we can go through and factor this into a plus b. So here's my a, here's my b, 4y plus 1. And then we're just going to go through and plug these in. So we're going to have 4y squared minus 4y times 1 plus 1 squared. So 4 squared is 16 y squared minus 4y plus 1. Alrighty. Questions on this, anybody? All right, so far we've had 3 formulas. I said we're going to look at 4, so we're going to look at one more. And this is the one that comes up from a common mistake that students tend to make. If we have a plus b squared, what students tend to think is that's here. I'm going to do this in red because this is bad. Don't do this. Is that's a squared plus b squared. Unfortunately, that doesn't work. And the reason because of that is, well, if we think about what it means to square something, that means we multiply it times itself. And we talked about this on Monday. What this really is this is a secret FOIL problem. which is, well, if we go through, first term here would be a squared. Outside here would be a times b. Inside here would be a times b. And then the last term would be b squared. So if we combine our like terms, we get a squared plus 2ab plus b squared. So the thing we're missing, and the thing that this is missing here, is this middle term that comes up. But the nice thing that happens is that if we're squaring it, these two terms are always going to be the exact same thing. So you're always going to have this double term. So what we can do is actually reverse engineer this a little bit as a way to simplify this, which is if here we have these perfect squares, right? This is a perfect square of A. This is a perfect square of B. And if that middle term is exactly double, then that tells me that we have this perfect square. And we can kind of bypass a bunch of factoring. So let's do an example. I'll kind of show you this works. And once again, technically these are trinomials. You could always go back to factoring these using a diamond, but a lot of times they're a lot easier to not do it that way. So let's do an example. So the key thing to notice here is we've got three terms, but my first and my last term are both perfect squares. First term is a perfect square of 2y. Last term is a perfect square of 5. So that's the individual, that's my a and b. If we multiply these two things together, that gives me 10y. And my middle term is exactly double that number. So what we could do is, instead of going through the full factor by grouping, doing the diamond, all that stuff, we can just say that this is going to be 2y plus 5 squared. Easy peasy. So once again, this is a shortcut. You could go through and do a diamond problem here. You know, 4 times 25 is 100. My bottom term is 20, so you can see that it's 10 and 10. You could go through and break up that middle term and work this one out. That one's not too terrible. But obviously, this method is a lot faster. So once again, it's a shortcut. Doesn't work all the time, but the times that it does saves you some decent amount of work, especially if the numbers are a little bit bigger. Let's look at this one. If you're doing this the old-fashioned way, you'd have to be, all right, well, there's no number that goes into 144, 120, and 25. So you'd have to go through and say, all right, well, the first times the last is 3,600. Oops, 3,600. And my bottom here is negative 20. We'd have to find two numbers that multiply to 3,600 but add to negative 120, which is real gross. I don't want to do that. So instead, what we'll say is, well, thankfully, these are both perfect squares. This is a perfect square of 12x. This is a perfect square of 5. Those multiply together to give us 60x, and my middle term here is exactly double. The only difference here is, oh, there's this minus here, which is fine. If there's a minus, all that means is I'm going to go 12x minus 5 squared. And that's it. So just to give this a name and to properly write this formula, if you have a squared plus 2ab plus b squared. This is what is called a, we're not clever when we name things, it's a perfect square binomial. And it comes from the fact that a, b, and my actual binomial are all perfect squares. Alrighty, are there any questions on this? Okay, so what I'm going to do is, technically I'm covering section 5.7, but really all you don't have homework for this. All 5.7 is kind of just a wrap up of the factoring that we've looked at. So today we've looked at 5.4, 5.5, and 5.6. Pretty much it's a factor wrap up. So what I'm just going to do is just kind of write it down as just kind of, all right, in general, factoring overview. And I'm just going to put everything we've kind of talked about on a nice little one-page thing you can kind of take a screenshot of. And this is going to work anytime I ask you to factor. If you consult this page, it's going to be everything. So when you're factoring, your first step is to always pull out any GCF. So is there anything that I can factor out of the entire expression? That's always step one, because it makes your numbers easier and it'll also set you up for your other factoring formulas. Okay, so from there, you're going to have two options. You're either going to have 2 terms, 3 terms, or 4 terms. If you have 4 terms, that's always just factor by grouping. Anytime you're asked to factor and you've got 4 terms, you're going to use grouping on that every single time. If you've got 2 terms, you're either going to have a difference of squares, so a squared minus b squared, which was our formula of a minus b, a plus b. Or, actually, I'm trying to leave this all on the page at the same time. Or you could have either a difference of cubes or a sum of cubes. So the difference of cubes was given by a minus b times a squared plus ab plus b squared. Or you have a sum of cubes, which factors into a plus b, and then you have a squared minus ab plus b squared. And those are all of your 2-term options. Technically speaking, we can keep going here. There actually is a formula for a to the 4th minus b to the 4th, but we're not going to go that high. Cubes is good enough for us. If you have 3 terms, it's either that perfect square trinomial, which is, remember, a squared plus 2ab plus b squared. So you have perfect squares. So that's that a plus b squared. Or it's a diamond problem. And this is it. This is literally anytime you need to factor, this is the step-by-step guide. First, plot any GCF, and then 2, depending on which terms you have, that's going to focus you into these following techniques. And there's no overlap here. There's no way you could have 2 terms and 3 terms. You have one or the other. So it's a nice little way to kind of focus exactly what we're dealing with. Because usually, for a lot of the problems, the only prompt is to just factor everything. And since we have so many ways now to do factoring, that can be kind of difficult to see. Okay, so let's do a couple of examples where we're just going to see, once again, the prompt for each one of these is just going to be to factor. And actually, I'm going to kind of scooch this up a little bit in the effort to get as much on the page as possible. And this guy got a little chopped off some of this. Okay. So let's say we have the following. Once again, we're just going to, the prompt for all of these is just going to be to factor. So let's look at the first one. 9x squared. Sorry, pardon me. Well, okay, I gave it away a little bit, but 18x squared plus 84x plus 98. So the first thing you always want to do is see, is there anything that we can factor out of the entire expression? Is there either a number or a term that goes into everything? And we see, so this is kind of that step one, pull out any GCF. And in this case, we have a factor of 2 that we can pull out. So when you do that, that's going to give you 9x squared plus 42x plus 49. So now we're looking to see, okay, how many terms does this thing have? And the answer is 3. So we're in the 3-term column. And so we're either doing a diamond or, well, do we have perfect squares? And in this case, we do have perfect squares. This is a perfect square of 3x. This is a perfect square of 7. Those multiply together to give us 21x, and the middle term here is exactly double. Oops, looks like I spelled double. So we can actually use my formula here, which just says, all right, this is just going to factor into 2 times 3x plus 7 squared. All righty. Questions on this example, anybody? All right, let's do one more. Okay, so you're initially saying like, oh, we've got cubes, so we must be looking at the cube formula. But 72 is not a perfect cube, and also x is not being cubed here. So the first thing is always you want to see, can we pull out a common factor? And in this case, both of these terms have a factor of 8, and both of these terms have an x on them. So I can factor that out. And then that leaves me with an x squared minus 9. So we still have our 2 terms here, but it turns out that this was actually a difference of squares. So this is a perfect square of x, perfect square of 3. So we can factor this into 8x times x minus 3, x plus 3. This is kind of the, once again, always make sure that your first step is to always pull out any common factors because one, it'll make things easier in terms of numbers. Two, honestly, at this stage, we have two terms, but we didn't have any of my formulas there because we didn't have perfect squares. We had a cube and a first power, and that didn't fit any of my formulas. So sometimes pulling out that greatest common factor is necessary to make us fall into one of our formulas. All right. So like I said, this is technically, if you want, this is technically in 5.7. You're not going to have any homework from it. And really all it is just kind of a review of all this stuff. So, working through the 5.6 homework is more than enough. But this is kind of a good little overview of here's everything that, if I say the words factor, this is everything that could possibly happen. Oops, not that guy. All right. So that being said, any questions on this stuff? All right. This is going to do it for us today. Just as a note, we don't have any homework this week due, so that means we don't have a quiz this week. So next week we will come back on Wednesday with some homework that's due, and also the quiz will happen next week. Okay. I'll stick around as always. People have questions. If not, have a lovely evening, and I will see you back here next week.
Thank you, sir.
Thank you. Have a good day.
You too.
Thank you.
You're welcome. Have a good one.
You too.